We ended our last video on a bit of a cliffhanger. We had seen that the exponential function, for example, let's say f of x equals a to the x, where a is greater than 1, so a is just some real fixed whole number greater than, or not whole number, but some real fixed number greater than 1. And we had said that because this function's 1 to 1, it has to have an inverse, and so the inverse should look something like this. Now this doesn't look like any of the graphs we've seen before, so the question is, what is it? Well, as it turns out, because it's something we've never seen before, we have to come up with a new name just to express what the inverse of the exponential function is, and we call that the logarithmic function. So the logarithmic function is defined to be the inverse function of the exponential function. Now, here's something you need to know about this logarithmic function. We understand what an inverse function is sort of intuitively, right? Remember, an inverse function essentially undoes a function. So if your original function is f of x equals x squared, then the inverse function would have to be square root of x, because when we compose these functions, right, square root of x squared, you get back your original input of x. Or we could even do this the other way around and say, if you take the square root of x and square it, you get back your original x. Similarly, the inverse function of x cubed is going to be the cubed root of x, because when you take the cubed root of x cubed, you get back your x term, or alternately, if you take the cubed root of x and raise it to the third power, you get that x back out again. Right? So inverse functions need to undo the work of a particular function, which means, let me erase this to make a little bit of space here. Saying that the inverse function of the function a to the x is f inverse of x is equal to log base a of x means it has to be the case that log base a of a to the x is equal to x, and similarly a raised to the log base a of x equals x. In other words, if you compose these two functions, if you plug one function into the other, they cancel each other out and just leave you with your original x. So with that in mind, let's define this logarithmic function a little bit more carefully. So let's assume that x is greater than 0. We'll come back to that in a minute. That a is some non-zero or some number greater than 0 and not equal to 1. Right? This is what we had already stated for exponential functions. Then we define log base a of x to be equal to y if and only if a raised to the y is equal to x. In other words, if you can take the base and raise it to the power of y, you need to get whatever's on the inside. That's your x. Right? So a raised to the y has to equal x. Okay, so the function log base a of x is called the logarithmic function with base a. So let's try to compute this and get a sense of what this is equal to. Alright, if we're trying to compute log base 2 of 8, it's going to be equal to some number that we're looking for. And using this definition over here, whatever that is, whatever that thing is that we're looking for, it has to be the case that 2 raised to that number, that question mark, is equal to 8. So you should be thinking to yourself, what do I need to raise 2 to the power of to get 8? That's going to be your answer. Well, 2 cubed is equal to 8. So that question mark that we're looking for here, that's going to be 3. So log base 2 of 8 is equal to 3, and that's because 2 to the third power is equal to 8. Let's try to use similar reasoning here. If we want to compute log base 3 of 9, we should be thinking to ourselves, all right, we're trying to figure out what this is. We need 3 raised to some power to be equal to 9. All right, well, what do you have to raise 3 to the power of to get 9? 2, right? 3 squared is equal to 9. And so that question mark that we're looking for, that's going to be 2. So log base 3 of 9 is equal to 2, and that's because 3 squared is equal to 9. Right, so we're just using the definition up above to try and get a sense of what these logarithmic functions are doing. So these log functions are sort of taking larger numbers and in a sense kind of truncating them. And notice also that these solutions here, 2 and 3, these are really representing exponents. You should be thinking to yourself, what exponent do I raise the base to get whatever's on the inside? Okay, let's try a few more examples. If this is a logarithmic function, say f of x is equal to log base 2 of x, and we want to evaluate the function for a particular x value, well, f of, in this case, x is equal to 32. So f of 32 should be equal to log base 2 of 32. So let's do what we were doing before. We're trying to figure out what this should be. You should be thinking to yourself, what do I have to raise the base, that's 2, to the power of to get 32? 2 raised to what power is equal to 32? Well, that's going to be 5, right? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So you need exactly 5 factors of 2 there. Okay, and so f of 32 is going to be log base 2 of 32, which is 5. And that's because 2 to the 5th power is 32. Let's do another example. Let's say we want to compute f of 1 for the function f of x equals log base 3 of x. So we want to compute f of 1. That is, we're going to need log base 3 of 1. Alright, now, again, we should be thinking to ourselves, what power do I have to raise 3 to get an output of 1? This one's a little bit different, right? What do I have to raise 3 to the power of to get 1? Actually, there's only one solution that will work here, and that would be 3 to the 0 power. Right? Any non-zero number to the 0 power is equal to 1, and so that exponent that we're looking for is 0. So f of 1 is going to be equal to 0 because 3 to the 0 power is equal to 1. Alright, let's try one more example. This one's a little bit tricky. We want to find f of 2 for the function f of x is equal to log base 4 of x. So log base 4 of 2 is what we're looking for. Okay, now here's what you need to think to yourself. What do I need to raise 4 to the power of to get 2? Right, this is different because, we're starting with a base that's larger than our output. So somehow this exponent needs to make my number smaller. Well, that's going to work if you use fractional exponents. Right? For example, we know that the square root of 4 is equal to 2. And so another way of writing this is to say 4 to the 1/2 power is equal to 2. And so that exponent that we're looking for is going to be 1/2. Thus, log base 4 of 2 is equal to 1/2. And that's because 4 raised to the 1/2 power is equal to 2. In other words, the square root of 4 is equal to 2. Okay. Now, what do we know about the graphs of logarithmic functions? Well, what we know is that log functions and exponential functions are inverses of each other. And so we can figure out the graph of a logarithmic function by just looking at the exponential function of that base. So let's start with the graph of 2 to the x. We did this a lot in the last video. Remember, the function 2 to the x has a y-intercept at 1. This is 2 to the x. And it's got a horizontal asymptote as x goes to negative infinity. The outputs are approaching 0. And so any inverse function can be found by reflecting over the dotted line y equals x. So when we reflect over this dotted line, instead of having a point at 0, 1, we'll have a point here at 1, 0. And instead of having a horizontal asymptote at 0, now we'll have a vertical asymptote at 0. And so when you reflect it, your graph looks like this. This is your function. We're calling it g of x, which is log base 2 of x. So in general, this is what the general picture of log base a of x will look like as long as a is greater than 1. This is a basic line that we're looking for, the basic curve that we're looking for. Some things to notice about this curve: it has a vertical asymptote at x equals 0. And notice that there's actually no values of the function at all for negative x values. Right? The function never crosses this line. It's just not defined for any negative x values, which means the domain of this function is going to be all real numbers that are strictly greater than 0. So we could write that using the open interval from 0 to infinity. Now, a couple of notation points. Oftentimes you'll see in books that will write ln of x to mean log base e of x. It's just shorthand. These mean the exact same things. Where e is that special number that we talked about in previous sections. It's equal to roughly 2.718, but it's irrational, so it'll go on forever. We also write log of x without specifying a base to mean log base 10 of x. It's just a shorthand because these are the most common bases that you'll see. And so if you see log of x without a base specified, you can assume the base is 10. And if you see ln of x, that means that it's a log function with a base of e. Alright, now, just like e of x was a really important function to us in calculus, ln of x is going to be really important because it's the inverse of the function, call it g of x, which is e to the x, right? Because this is log base e of x, so the inverse would be e to the x. Right, now remember, let's make this a little bit bigger. The e to the x function looks like this. Looks a lot like 2 to the x, but it just grows a little quicker. Y-intercept at 1. It's got a horizontal asymptote at 0 as x goes to negative infinity. And so just like before, we get this inverse function, ln of x, whose graph looks like this. A vertical asymptote at x equals 0, and then it grows a little bit more slowly. So this is a graph of ln of x, and the green curve is a graph of e to the x. Now, what is the domain of f, of the red one, of the log function ln of x? Just like before, the domain's going to be all real numbers greater than 0, because this function's not defined at x equals 0, and it's not defined for any negative x values. What's the range of this function going to be? Well, what outputs do you get? You get every possible output. Another way of thinking of this is that for the g function, that's the e to the x function. Remember, this has domain of all real numbers and range of 0 to infinity. And so for the inverse of this, the domain and the range should be swapped. So for this function ln of x, we had seen that the domain is now 0 to infinity, and so the range should be all real numbers. Now what about the end behavior? Remember that e to the x had a horizontal asymptote as x goes to negative infinity. This doesn't have any horizontal asymptotes. It's going to keep approaching infinity as x goes to infinity. So let me make a note down here at the bottom. Save some space here. For end behavior, as x goes to infinity, our function f of x, ln of x, is going to also go towards infinity. It goes slowly, but it still goes towards infinity. We can't really talk about what happens to this function as x goes to negative infinity, because the natural log function isn't defined for negative values at all. But we can say that as x approaches 0, I'm going to put a plus sign here to mean from the positive side, because it's not defined for negative values. We have that f of x approaches 0. I'm sorry. Yeah, your outputs are heading down here towards negative infinity, right? You have a vertical asymptote at 0. Right, so f of x equals ln of x has a vertical asymptote at 0. Okay, let's do a few more examples. We're going to find the domain of each of the following functions. So these are ln functions that have been changed around in some way. So for example, ln of x minus 2 or ln of 2 minus x or ln of x squared. Now remember that in general for any log function, we need whatever's inside the parentheses to be positive, because log functions are only defined for positive x values. They're not defined when x is equal to 0, and they're not defined for negative x values. So we can find the domain of each of these functions by just taking what's inside the parentheses, I have that as dot 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 here, and making sure it's strictly positive. That is, making sure it's greater than 0. So for this first example, I have ln of x minus 2. I identify what's inside the parentheses, that's x minus 2. I set it greater than 0 and then solve. Okay, this is just the linear inequality. I add 2 to both sides and I get x has to be greater than 2. So the x values that are greater than 2 can be expressed in interval notation as 2 to infinity. Alright, let's try number 2. This time we have ln of 2 minus x. So I'm going to identify what's inside the parentheses. That's 2 minus x, and set it greater than 0. Again, I'm going to solve this. I'm going to add x to both sides so I don't have to deal with any negatives, and I get 2 has to be greater than x, or I could express this as x is less than 2. Alright, so for this one, my domain is going to be all real numbers from negative infinity to 2, because x needs to be less than 2. Alright, finally, for number 3, identify what's inside the ln function. That's going to be x squared. I need x squared to be strictly greater than 0. Well, when is x squared strictly greater than 0? Remember, when you square a non-zero number, it's going to become positive right away. It's just going to naturally be greater than 0, right? Because a negative times a negative is positive, and a positive times a positive is positive. So the only time that this isn't true, the only time this inequality fails, is when x is equal to 0. And so our domain is just, this is going to be defined for all real numbers except when x is equal to 0. So our domain can be written in interval notation as negative infinity to 0, union 0 to infinity. So it's all real numbers except for 0.